This is a water jetpack. But no, that's not me flying it. This is me. It's harder than it looks, okay? But to understand how it works, we need to first talk rocket science. Rocket science is meant to be one of the most complicated things in the world, but the basic principle is incredibly simple. It's just Newton's third law. All forces come in pairs, which are equal and opposite. To demonstrate this, I'm using a fire extinguisher on a skateboard. As the carbon dioxide is forced out the back of the extinguisher, it puts a force forwards on me, causing me to accelerate. Or that's the theory anyway. If you look closely, you can spot the exact moment I realized this is a fail. So what was the problem here? Well, the force applied to me by the carbon dioxide is equal to the rate of mass ejected out the back of the fire extinguisher, call it m dot for short, multiplied by the velocity of that exhaust gas. So in this case, the carbon dioxide wasn't ejected fast enough to create a big enough force and overcome the small frictional forces to get me to accelerate. But it can be done, as has been demonstrated many times on YouTube. When the space shuttle lifts off, exhaust gases exit the nozzle at 3 to 4 kilometers per second, ejecting an amount of mass of 9,000 kilograms per second. This creates thrust equal to 30 million newtons, or the equivalent of about 2 million decent fire extinguishers. Now, imagine you're an astronaut preparing for launch in the space shuttle. You would be seated not vertically, but horizontally, perpendicular to the acceleration. And that's because the human body is a little bit like a water balloon, where the water represents your blood and the balloon represents your harder parts like your skeleton. Now, if you're accelerated up really quickly, then your skeleton accelerates up at that rate, but your blood tends to stay where it is. And this results in the blood ending up in your feet. Now, since there's not enough oxygen going to your brain, you would black out. But fighter pilots face an arguably worse fate when they accelerate down too fast, because then the blood all rushes to their head and they suffer something called a readout, where the blood actually comes out of their eyes, nose, mouth, and ears. But back to astronauts. Since you reclined, at worst the blood will end up in the back of your body and the back of your head, but your brain will still have enough oxygen to remain conscious. Now, as the spacecraft lifts off and starts speeding up, the acceleration is initially a very reasonable 5 to 8 meters per second squared. That's less acceleration than an object in free fall here at the surface of Earth. But as the spacecraft continues to burn fuel, its mass decreases, while the thrust remains essentially constant. Now, Newton's second law says that the acceleration of an object equals the net force applied to it divided by its mass. So as the mass decreases, the acceleration increases. And it increases at an increasing rate. So much so that at the end of the rocket burn, the thrust has to actually be limited in order to keep the acceleration from going over 3 Gs. That's 3 times the acceleration due to gravity, or about 30 meters per second squared. Now, the term G-force has been invented to give a sense of the amount of force experienced by astronauts in multiples of the force we experience every day. Right now, you're experiencing 1 G-force, probably on your butt if you're sitting down. Can you feel that force? But accelerating at 3 Gs, you would experience 3 G-forces. So the force between your back and the chair would be the same as if you had 2 of you stacked on top of you. Oh!
Hey, pipe down below, huh?
Oh, you guys are heavy. Oh man. You know that feeling when you're taking off in a plane and it feels like you're pressed into the seat? Well, really, it's the seat pressing into you. But if you imagine that feeling times 20, that's what it would be like to be taking off in the space shuttle. Now, an interesting little side note is that we think of the space shuttle's acceleration as being mainly vertical because that's what we see when it lifts off. But that's actually not true. Once the space shuttle exits the thicker part of the atmosphere, it turns horizontal and accelerates up to its orbital velocity of 28,000 kilometers per hour. So most of the acceleration of a spacecraft, in orbit anyway, is horizontal. So how is this like a jetpack? Well, unlike the shuttle, you don't carry your own propellant with you, and also there's no chemical reaction releasing energy that drives the propellant downwards. Instead, the jet ski pumps water out of the lake and up that hose at a rate up to 60 liters per second. And then right on these nozzles here, the water changes direction, so it goes from coming up to being fired out the bottom, and that change in momentum as it goes over the bend is what actually pushes the jetpack up, because the jetpack's pushing down on the water. So by Newton's third law, the water has to push up on the jetpack, generating 1,800 newtons of thrust. That's roughly equivalent to 150 decent fire extinguishers. This could accelerate me at up to 1.5 Gs. And you use your hands in order to steer, lifting up to drive yourself upwards, moving your hands down to accelerate forwards, and pretend like you're turning a big wheel very gently in order to turn side to side. One thing you don't want to do is try to explain the physics of the jetpack while in the air. That's what I was trying to do here. While you're learning, your thrust is controlled by your instructor. So if he sees you doing something stupid, he'll just turn off the thrust and drop you into the lake so you don't hurt yourself. That's generally a good idea unless you're on a collision course with the jet ski. I got a pretty fat lip from doing this, but luckily all my teeth were intact. When the thrust is equal to my weight plus the weight of water in the hose, then I can hover or move with constant velocity. It's a common misconception that you need a little bit of unbalanced force to move with a constant velocity. In truth, if the forces are balanced, you will just continue moving with whatever constant velocity you have. The other common misconception about rockets is that you need something to push off like the atmosphere. In reality, what you're pushing off is the propellant. So even without the air around, a water jetpack would still work because you're pushing off the water that is coming out of those nozzles. If you want to go jetpacking, I recommend you go easy on the controls. I mean, the worst thing you can do is overcompensate, which I think is a typical human reaction, because you're reacting to where you are and how fast you're moving, and you're not reacting to acceleration, which is the real thing that you can control. So even if you're coming down towards the water quite quickly, you may be slowing down, so it may be okay and you don't need to adjust anything. You just kind of need to trust that the jetpack will get you out of any trouble. It's a pretty incredible experience. Feeling the power of that water rushing past you. It's the closest I've gotten to flying, really. Yeah. It's the power of physics. Now, many of you may not know that I have a second channel called 2 Veritasium, and I've been posting more videos on there recently, so if you want to check them out, then click on this annotation or the link in the description. If you ever want to download a Veritasium video, you can do that now via iTunes by clicking this link, and that's a service provided to me by Science Alert, which is one of the greatest Facebook pages on science that exists. So click on this link if you want to check them out. All right, thanks for watching.